system. He is a senior member of IEEE, Power and Energy Society, IEEE Industrial Application Society, and IEEE Smart Grid Community. So I hope he is the very apt person to handle the session. I request Dr.B.Chitti Babu sir to take over the session. Thank you.
Yeah, thank you very much for such a big introduction. It's a very impressive. Anyway, thank you very much. And still, I feel that I'm a student. I'm a beginner. I'm a researcher. So I'm going to deliver a talk on advanced control strategies for gridded solar PV system. So let me share my screen. Yeah. So hope video is not required. Yeah. Is it visible now?
Yes, sir. Is it visible?
Okay. Thank you very much. And a very good afternoon to one and all. Dear participants, a warm welcome for, I think, third day of Atal FDP on electrical vehicle. So I'm not going to deliver a talk on electrical vehicle. Instead, I am going to give a talk on advanced control strategies for grid integration of solar PV system. Of course, the control and integration of renewable energy or electrical vehicles, still the concept it remains same, only how the control strategies are going to be studied and implemented in a different platform. That matters a lot. Of course, the participants may get some kind of ignition and basics on the control strategies, how we can develop both in simulation and in the laboratory prototype to implement for any grid integrated renewable energy systems, particularly on solar PV system. So I have been with IIITDM Kanchipuram, Chennai. It is one of the institute of national importance and established by Ministry of Education, Government of India. So I have been with this institute since June 2018. And I have developed a laboratory called Photovoltaic Research Laboratory here in IIITDM Kanchipuram, Chennai, funded by DST ACRB. And we have developed 1 kilowatts grid connected solar PV system having a two-stage power converters, including DC to DC boost converter and three-phase two-level PWM VSI for integrating solar PV with the utility grid. As you might be knowing that the solar energy is a very promising source of energy as of today, in addition to wind energy conversion system. And these two key technologies are playing a very major role, especially on global warming as well as mitigating CO2 emissions. So with this aspect, I am particularly working on a solar PV system, and we have developed and we have made a laboratory prototype, and we have implemented and we have applied several control strategies for grid-tied solar PV system. And our team, we could be able to publish number of research papers, including IEEE transactions and IET and other reputed journals. So I'm going to share my research experience and our team, what we have done so far on this particular area. So I'm going to engage for next 2 hours. So hope the participants will understand, will get certain essence on control strategies for grid-tied solar PV system. The outline of my presentation that includes renewable energy in Indian scenario. Of course, we should have a common sense and we should have a kind of motivation that why renewable energies are playing a very major role, especially on the subcontinent India. And what would be the basics of PV cells and how the hierarchy of PV system is developed, and what are the main objectives of proposed research, and what we have done so far, how to design a grid interactive PV system, and that design that includes subsystem called power circuitry as well as control circuitry, how that has been fabricated in the laboratory prototype, how the proposed control algorithm has been implemented in a real time in addition to the mathematical modeling in MATLAB Simulink, how the experimental setup are made in the laboratory, especially to validate proposed control strategy. We could observe certain experimental validation with certain observations, so that there must be a convergence between the experimental as well as the simulation result. that will be concluded with certain remarks followed by the references what we came across in this particular area of research. Renewable energy in India. As all of us know that India is a developing country and we are the third largest consumers of electricity as well as the power producer in the world. As of September 2020, about 36% of the total installed capacity is from renewable energy sources. I mean, out of 373 gigawatts of total installed capacity, about 135 gigawatts of power as we meet from renewable power generation systems, especially on solar energy and wind energy conversion. By 2027, our target would be 57% of the total installed capacity by renewable energy sources, according to Central Electricity Authority, Government of India. And you can see that about 57% should be an total installed capacity by 2027. And you might be knowing that these two key technology, especially on photovoltaic and wind energy, they are playing a very major role. We are able to generate electricity in tens of megawatts level, and hence the systems are called basically a large scale power production systems in tens of megawatts. And India, it holds 4th rank in the wind power and 5th in the solar power and the 5th in the total renewable power installed capacity in 2018. But as of 2020, so we moved forward as we hold the 4th rank in the solar power and the 4th rank in the wind power as well. So of course, one can understand that how the research and development happens in India and how government has taken an effort to initiate and to promote renewable energy sources. And you might have seen that a number of states, they have devoted in developing renewable energy, particularly on solar photovoltaic, like Rajasthan and Gujarat, Maharashtra, even in Tamil Nadu and Karnataka. So they have taken an initiative and the effort to launch an e-power plant based on solar photovoltaic. And you can see that the total installed capacity by wind and solar, about 38,000 megawatts by wind and 36,000 about solar. As you can see, both are highly comparable as compared to other renewable energy sources, excluding large hydro. And among these two, wind power and solar power, the solar power is a fast developing industry. The country's solar installed capacity was about 44,300 megawatts as of 31st August 2021. So now totally solar power is dominating. The reason behind that, during 2000, 2010, during couple of decades, the wind energy was a very promising source of energy. And everywhere there was a huge development in a wind turbine system. And you might have seen, even especially in Tamil Nadu and the south part of Tamil Nadu, we could see number of wind power plants. So the wind energy system is very mature technology. It's well established technology that almost it is well established so that we could be able to feed power to the utility grid without having any problem. Integration. And the countries like India, we have developed grid code compliances as well to integrate wind power generation with the utility grid. And we have a large amount of wind potential. But during that era, the solar energy or solar power generation was not emerging, was not up to the mark because of capital investment. Now, thanks to material science and technology, that the solar PV, it holds a top rank among all renewable energy because of clean and green energy source. It is a pollution free. It doesn't cause any CO2 emissions, and moreover, the forecasting it's quite easy as compared to wind power generation, and that is what. So, and moreover, due to development in material science, the thin film technology and bifacial solar cells, so they are going to be commercialized in decade. So that the solar power generation, of course, the power generation cost, it would be almost comparable with the thermal power plant maybe after a decade. That is what. So we are mostly focusing on solar power generation. Still, it has an impact in the research and development as compared to wind energy conversion. And you can have an idea how we could be able to get the motivation on the solar photovoltaic. You can see that there is a place in Rajasthan about Batla Solar Park, which is the largest solar PV power plant in the world. It's about the fully operational with capacity of 2,250 megawatts of power. This huge solar power plant was developed by Rajasthan Solar Park Limited. Almost the power consumption almost 10% solely made by this power plant. And almost you can see the second one is Shakti Shatla solar power plant. It's about 2000 megawatts. It's a Tumakuru district in Karnataka that has been launched recently. And again, there is an ultra mega solar park about 1000 megawatts in the Kurnool district, Andhra Pradesh. And there would be a Reva solar power project about 750 megawatts in Madhya Pradesh, and Kamuti solar power plant here in Tamil Nadu about 648 megawatts of power. So these are the top plant that has been installed in India. And you understand that, and you see the solar park, how they made it about almost, I think, 400 acres they have launched, and they have made this PV array to have a maximum and the full rated capacity of 2,250 megawatts of power. And the main advantage of the solar PV, as all of us know, that it doesn't have any movable part. The solar PV array is made up of simple PN junction semiconductor cell. It is made up of silicon semiconductor. So the design time or the design is quite easy. That can be easily installed at a site. And so the startup of a new plant is quite easy than the wind turbine, because for a wind turbine about 2000 for 2 megawatts or 5 megawatts single wind turbine, the transportation and starting up and installing it's very difficult. But here the design and installation is very simple as compared to wind turbine, and it is very modular structure. It has a very modular structure, and moreover the power output matches very well with the peak load demand. That is what during hot summer we have good irradiation. So due to larger irradiation during hot summer, the power output, it's the extraction from the PV is more. That is what it is exactly matches with the peak load demand, as it has a bell-shaped characteristic curve, and according to the time slot. And during afternoon, I mean during this time interval, you can see that the power output is maximum during this time interval. Okay, power output is maximum. So because of that, the mostly during hot summer we are able to generate more electricity by installing the solar plant. And as it has a static structure, there is no movable part, hence no noise. It's very clean and green energy source. And moreover, it has a high power capability per unit of weight because of such a materials as we are going to use, longer lifespan, and because of portable as well. But the disadvantage of solar PV is that anybody can say that the conversion efficiency is very low, not even 20%. It is a theoretical efficiency. So practically the solar cell, it never operates, not even in 15% in the real PV panel that has been installed in any site. All right, because we are converting low quality light energy to high quality electrical energy. Of course, it obeys second law of thermodynamics, that whenever there is a transformation of low quality energy into high quality energy, it is impossible to achieve 100% efficiency even in theoretical maximum limit, right? So with that, the conversion efficiency is very low. That is what we invest a huge investment for generating an electricity with the help of solar PV system. But now, thanks to material science, we have such a material or such a technology called bifacial solar panel. So you can see that the PV panel, the PV cells are fabricated on top of the panel as well as the bottom of the panel. Now what happens when this PV panel is exposed to the sun? When the PV panel is exposed to the sun, then the irradiations are falling on the top of the panel as well as bottom of the panel due to floor reflection. So this reflection is this flooring. If the flooring is completely filled with ice, like a heavy snow in the Western countries like Europe or Canada. So if these panels are installed, then the floor with the huge ice or snow, it is a good surface to have a tendency to reflect more photons or more irradiance towards the bottom of the panel, so that the conversion efficiency will be doubled. So this is one of the mature tech. It is a developing technology in the solar PV system that is we are trying to enhance the efficiency, and moreover now the multi junction solar cells are in are in under development, and also it is a compound semiconductor material. They use like a indium phosphide or gallium arsenide phosphide. Likewise, if you combination of two or more semiconductors, they are going to fabricate for generating an electricity with the help of solar PV panel. Of course, cost is going to be reduced, and a variable energy source. This is one of the difficulty encountered in solar PV. Energy source is variable. It implies that the input power to the PV panel is basically a temperature and irradiation. So they are the two state of art of the solar energy. You know, solar energy is a universe of energy. As you transmit light and temperature, and then this light energy is falling on the surface of the solar panel or the solar cell, then there would be an electron hole pair recombination. Then there is a possibility of generation of electron, and the effect is what is called a solar photovoltaic effect, right? So the output voltage or output current, it largely depends on the input parameter. All of us know that output is time dependent of input. As all of us know, electrically of any electrical system, output is basically a function of input. So that input is basically temperature and irradiation. So due to changes in temperature and irradiation, output power changes. So that as the output power changes, this cannot be directly given to any electrical load. As it is a DC energy source, this cannot be directly connected to the battery. As the battery, it needs constant voltage for charging. Due to variable voltage, then the battery will be overheated, and that may damage your battery due to excess heat produced inside the battery, right? These are the important cons of a solar PV system. And this is the very simple concept of the PV cell, that when the PV panel is or PV cell is exposed to the sun, and then the solar irradiation, that is called photons and light falling on the surface, as it gets a metallic conducting strips that, and it is able to collect the electron. And when you connect an external electrical load, then there is a possibility of current flow, right? So simply converting light energy into electrical energy with the help of photovoltaic effect, as all of us know the basics. But here what I mean to say is that the electron flow or the current flowing towards the external load, that is called output of the PV panel, it depends on the solar irradiation. So as the temperature or the irradiation changes, of course the output voltage and output current changes. Okay, that is what it is, basically a variable energy source or intermittent energy source. And as you know that this is the very simple concept, that how it is able to produce electrical energy as an output, that all of us know that. As when the solar cell is said to be a constant current source at a low irradiation, there is no output current is produced, and hence then the cell is said to be open circuited. So during open circuit condition, there is no current, then the voltage is maximum. So this is the maximum voltage generated by any solar cell. That is what is called open circuit voltage. At large irradiation, then more photocurrent flows, and due to that the junction is said to be short circuited, so that the maximum current circulated in the short circuit, but the voltage, it remains zero. This is what is called a short circuit current. That's the maximum theoretical current. All right. So now change in irradiation or temperature, of course, it has a characteristics like this, right? So you can take a particular point or the tangent, that the corresponding voltage, it would be a maximum voltage. The corresponding point in the current is a maximum current, right? So the maximum current at a maximum voltage, multiply that, it gives the maximum power as what we are extracting from the solar PV. So this point, it always moving upwards or downwards, right? So due to change in irradiation and temperature, this point will shift upwards or downwards, so that you have to apply a kind of control circuit between the PV panel and the load, so that this point would be in equilibrium at any stage. Either change in irradiation and temperature, this point, it remains constant. That is what we employ an algorithm, what is called a maximum power point tracking, right? Usually during open circuit or during normal operating, the PV cell, it generates the voltage about 0.5 volt DC for a silicon solar cell. And however, the output current, it depends on intensity of the insolation and the size of the cell. I mean, intensity of insolation means incident solar radiation. The unit is watts per meter square. So if the irradiation changes, obviously current changes linearly, whereas the voltage, it remains constant or it changes slightly. That is what. So if the sun is available at during afternoon, then the irradiation is very high, then the current increases drastically, and hence the output power is maximum. That is what the thing. So the maximum power extracted or generated by the solar cell, it largely depends on irradiation. Okay, that is what. Usually solar cell, it works fine with high irradiation and low temperature. If the cell is exposed to high temperature, then drastically it reduces the voltage and hence the output power degrades. So that is what always solar cell performs better during large irradiation with low temperature. Keep in mind that, right? And yeah, this is what at a particular irradiation, and you can see the current is minimum. In the irradiation changes, then the current is increases, right? And this is the point at which we are extracting maximum power. The multiplying, the corresponding voltage would be 0.49, corresponding current would be 4.95 ampere. So the multiplying 4.95 with 0.49, you get maximum. I mean, it is the practical power that has been generated by the solar PV. But theoretically, the maximum power is the multiplication of short circuit current and open circuit voltage. That is 0.62 multiplied with 5.5 ampere. So taking into the consideration of practical design of any solar cell, this rectangular curve is very important. This rectangular curve, the area under this curve, that gives multiplication of Vm into Im. This is what is called a PM. That is a maximum power supplied by the solar PV. So this area under the curve is the maximum practical power that has been generated by the PV. 0.62 multiplied with 5.55, that is the theoretical maximum power that can be generated by the PV. So taking the ratio between the practical maximum power divided by theoretical maximum power is what is called the fill factor, and we can say that is simply FF, fill factor. So any solar cell, the fill factor that decides the overall performance of the cell, it should be always less than 1, between 0.6 and 0.8. So accordingly, solar cell has to be designed. So if you are trying to make this rectangular curve or par with these two position, then we can, this is what the multiplying these 2 points, right? So if this point is shifting towards here, then we can say the solar cell should be ideal solar cell or lossless solar cell. That cannot happen in real time, right? This is what the things. So the maximum power point is this one, right? The point at which we are able to extract maximum power, right? So it implies that, as I told you, the power extracted by the solar cell, that depends on the input parameter of the sun, input parameter of the solar panel, or the state of art of sun is basically in irradiation and temperature. So change in irradiation and temperature, the output power that the P max is shift upwards or downwards. So that we employ a conditioner or the circuit, what is called a power conditioner. So the power conditioner has to be incorporated between the PV panel and the load, so that this power conditioner, it will try to match an impedance of the resistance between the source and the load, so that it could able to fix the point in equilibrium condition. That concept is what is called a maximum power point tracking. For that, we need to have a power conditioner circuit, basically a DC to DC converter, right? So that we incorporate. This is what the characteristic resistance. So this resistance has to be adjusted according to the source resistance, so that we could be able to achieve maximum power point tracking by satisfying the theorem, what is called the maximum power transfer theorem, right? You can understand that. Yes, this is what the value chain for the PV energy. As the solar cell is basically a polysilicon material, as it has been originated from ingot, solar cell material called silicon. And with the help of ingot wafer preparation, then we are able to make the process of silicon melting and ingot glowing, and we are able to make the solar cell, right? That is what is called a silicon solar cell. which is made up of silicon with p-type and n-type that has been combined with the junction what is called a depletion region. Basically it is heavily doped, and by connecting number of cells in series parallel, and we get the PV model with the required rating. Further connecting number of PV model in series parallel, we can have a PV array that can be installed at the home, so that we can have a rooftop. I mean, in the roof, we have a PV on the rooftop with additional components called inverter, battery, and supporting system, so that this house can be powered by a solar PV system. Either this can be a standalone system or maybe a grid connected system. This is what the value chain for the PV energy. And the PV cell technologies, as all of us know, that solar cell is basically a semiconductor material. It is made up of either silicon semiconductor or compound semiconductor or maybe an organic semiconductor. Still, this is not so popular for electricity generation. Either we can use a silicon or compound semiconductor. And again, silicon semiconductor that has been classified into crystalline and monocrystalline and polycrystalline further. And non-crystalline is basically an amorphous silicon, but the conversion efficiency is very low. So this is also not popular for solar cell. The solar cell is basically made up of either silicon, single crystal, or polycrystal, having the conversion efficiency between 10 and 17%, 10 and 13%. So mostly monocrystalline silicon semiconductor solar cell is very popular. It is available in the market because the conversion efficiency is somewhat between 10 and 17%. But now another important material is it is emerging for the solar cell called compound semiconductors. So here we are able to combine two semiconductors, gallium and arsenide, called GaAs. So by incorporating two semiconductor material, we could be able to make compound semiconductor, so that we can enhance the conversion efficiency about 18 to 30%, because we are enhancing the energy band gap between valency and conduction band. You know, increasing the energy band, obviously it produces more output voltage, and then hence the output power is maximum, so that the conversion efficiency is maximum, right? So the conversion efficiency is basically a ratio between electric energy output by energy of insolation on the cell. Then you know how the efficiency conversion takes place in the cell. This is what the hierarchy. Cell is simply a single silicon cell having a power range between 2 to 3 watts and having output voltage of 0.5 volt, about the current of 5 to 6 ampere. But still number of cells are in parallel, having the output power of 2 to 3 watts. The size would be about 10 centimeters square. And the model, here the model mean about 6 and 9, about 54 cells are connected in series parallel, having the power rating between 100 to 200 watts. Further, 100 to 300 models are connected in series parallel to have a PV array for the rating between 10 and 50 kilowatts. So this is what the hierarchy of the PV system. So someone can understand that solar cell, solar PV model, PV panel, and a PV array. And further, that the PV array will be again connected in the, installed at the site with again series parallel, so that we can have a solar park. So that solar park, the output power would be in terms of kilowatts or megawatts level. Let us come to a motivation about the research work and what we have done. That as all of us know that that you can see here, as the number of PV arrays are connected in parallel and series to have a required power rating between 10 and 15 kilowatts, 50 kilowatts, right? So we wanted to feed this generated output power of the PV to utility grid, right? So utility grid is basically an AC grid. You know that the grid is an AC component having fundamental frequency of 50 hertz, but the solar PV, it generates a variable DC power, because is basically a variable DC source, because the output power, it depends on the input parameters like temperature and irradiation. So at every moment, climate change that cause the change in temperature and irradiation, and hence the output power changes. So that variable DC power or uncontrollable DC power, that cannot be fed directly to the utility grid, whereas the grid is an AC component. Obviously, we need, there is a converter between a solar PV and the utility grid. So in a grid connected system, the main consideration is to design and operation of the power converter to achieve high efficiency for different power configuration. So overall conversion efficiency system efficiency should be high enough. That is the very important thing about the things. So while integrating solar PV with the utility grid, so that the power producer has to meet certain requirements that has been imposed by a power system operator or transmission system operator, that is called a TSO. So TSO, they impose certain requirements of a power producer so that they could be able to accept the power that has been generated by a particular company, right? So that requirements are called grid connection requirements or grid code compliances. Talk about grid code compliances of America, they have a US grid code compliances. Canada, they have a Canadian grid code compliances. China, they have a Chinese grid code compliances. Ireland, they have Irish grid code compliances. Almost all countries, they have their own grid code compliances to integrate solar PV with utility grid or wind energy system with utility grid. So that requirements are very important. By satisfying that requirements, we are able to integrate solar power with utility grid. So that requirements include maximum power extraction. First of all, solar PV is a low energy conversion device or low efficiency energy conversion device. So that has to be extracted with the maximum power level by employing maximum power point tracking. So the maximum power extraction is very important, and it should have a high efficiency. It should have a high efficiency, mean overall conversion efficiency should be very high, more than 90%. And moreover, the power that will be injected into the utility grid, that must be controllable. Controllable means in terms of active and reactive power. All of us know that the active power and reactive power must be controlled independently, must be controlled instantaneously in order to control or in order to regulate both grid voltage and grid frequency. Because grid voltage is very essential to maintain the voltage profile constant. Reactive power control is essential to maintain the voltage profile constant. Active power control is very essential to maintain the frequency remain constant, because frequency is a key parameter that governs power system security, and voltage profile is a key component that governs power system reliability. So that is what the main motivation of grid connection requirements, that includes controllable active and reactive power that must be injected into the utility grid. And it should have a lower total harmonic distortion, because as we use the inverter, of course it is inherent property with non-linear and PWM switching, and again we have a non-linear electronic load that will be connected at the point of common coupling. So due to nature of the load, due to nature of the inverter, inherently the output current of the inverter, it contains harmonics, lower order harmonics. So that we have to employ a control technique on this inverter in order to reduce the harmonic current that presents on the inverter output side, right? So ultimately the grid current should have a lower THD, lower total harmonic distortion. So as per IEEE 519/2014 standard, it should have a THD of less than 5%. And further, it should have an excellent transient response. So the transient response is very essential, that it ensures grid stability. When the grid is under abnormal condition, still the grid, it should have a stability to sustain when the grid is under abnormal condition. Of course, it needs kind of fault right through capability. Still, the energy can be restored without any interruption. And further, the grid synchronization is very essential to match the inverter output frequency with the grid frequency. So both frequency must be synchronized at a fundamental frequency, what is called a 50 Hz. Then we can have a possibility of successful integration. This is what the key motivation about grid integration of solar PV system. So the similar procedure should be followed while the vehicle is integrated via the inverter system. How the vehicle dynamics are involving. So in terms of controlling the vehicle speed as well as the torque, so that the speed and torque control must be independent with each other. Of course, it needs a control of active and reactive power. Of course, you are able to control the inverter output voltage and current so that we are able to meet the dynamics of the load, that is called the electrical vehicle, so that the successful integration is possible with the utility grid. So the similar approaches can be followed even for grid integration of plug-in electrical vehicle as well, right? So consequently, the requirements of grid connection, called the grid connection requirements, that will be that it largely depends on the control strategy applied on the inverter. Right. So consequently, the performance of the converter connected to the grid, it largely depends on the control strategy applied. That is what our motivation behind the grid integration of solar PV system is to develop an advanced control technique. So with the help of such advanced, robust control technique, we are able to successfully integrate solar PV system with the utility grid. So the objectives of the presentation that include design, development, and implementation of grid interactive PV system. So we have developed a laboratory prototype of three-phase, three-legged inverter as well as three-phase, four-legged inverter. And this inverter is configured as a multifunctional inverter. So it implies that multifunctional inverter not only control an active and reactive power in order to maintain the voltage and frequency, that also contribute or that can also access a active power filter. So it serves as an active power filter for power quality improvement when we connect a nonlinear load at the point of common coupling. So proposed system that provides power quality improvement features under nonlinear and unbalanced power electronic based loads connected at the point of common coupling. And it also contributes for active power sharing. So there will be an excellent energy management system. Right. So these are the important objectives of the presentation. As we all of us know that increasing application of power electronics is very vital, especially in power system, because the availability of high power semiconductor devices as the decentralized renewable energy generation system, that is called a distributed generation system. Virtually we are eliminating a transmission line so that overall system efficiency is very good, and moreover the voltage regulation is excellent in the distributed generation system. And with the reactive power support, increase the power transfer capability of the existing transmission system and the effective control of power flow, that is active and reactive power flow control, in addition to the norms for power quality. So the future power system would be like this. Having the common control center, we are able to control all the components, including energy and the energy storage and other stations as well. Right. So mostly we employ a power electronics converter between the source and the load in order to improve the source dynamics and also to improve the load dynamics. Of course, we should have a power electronics converter that provide an asynchronous interface between the solar source and the load, so that we could maintain the good dynamics between the source and the load, because load is a variable one, and again source is also variable, or it is random in nature. Of course, we need to have a power electronics converter with suitable controller. These are the listing of power electronics application. Simply I can say that there is no power electronics, there is no modern power system. Of course, power electronics, it became a very vital, it became a it became a part of power system. That is, it's a heart of modern power system. So that holds to have a proper power flow, to have an energy management, to enhance the lifetime of the all electrical equipment. Of course, we need power electronics converter, starting from your mobile phone. As your mobile phone power management ICs are working under the principle of power electronics, even that manipulates the power in terms of milliwatts and microwatts level up to multi-megawatts wind turbine system. We use invariably power electronics, either in the distributed generation or maybe power electronics load with the ASD or variable speed drive or power quality solution. We use the custom power devices, or we use the fax devices for enhancing the performance of transmission and distribution system, including HVDC transmission, right? So these are the different applications of power electronics. And still we face difficulty in modern power system as well, because of there is a complexity in the traditional power system, and moreover there is a problem associated with the system stability, that the renewable energy sources are basically a fragile energy sources. So fragile energy sources mean they doesn't have any inertia. So due to inertia-less property of the solar energy or the wind energy conversion system, so it cannot damp out any oscillations, either it occurs internally or externally. That is the problem associated with renewable energy sources. We inherently use energy storage system to improve the renewable energy system or to provide a virtual energy. That is what the system, it become distributed generation. Distributed generation means renewable power generation plus energy storage system. That is what now you might be knowing that energy storage is another emerging area of research in modern power system, in addition to renewable energy generation as well. And moreover, now due to emerging of electrical vehicle, and you might be knowing there is a vital role of energy storage elements in electrical vehicle as well, because the battery has to be charged so that it is able to drive your electrical vehicle for a time time, then again once it discharges, again it needs charging. That is what. So energy storage, it became a very important component in modern power system. So that your vehicle or any renewable energy sources, it needs an auxiliary requirements with the help of energy storage. Until now, we are fixing the problem of power distribution. We never find the exact solution. That is what we are working on, that particular area of research and development. And the challenge is what? Mainly finding the solution which should be very cost effective. That is not possible, right? And moreover, increasing the efficiency of the overall system is a very difficult task, because the power generation itself low conversion efficiency. For say talk about wind turbine system, the conversion efficiency not even 40 to 50%, and conversion efficiency of solar is not even 20%. Of course, the enhancing the overall efficiency of the system, of course, it needs have an effort to install such a high performance power electronics converter system. Obviously, it increases the overall cost of the system, and over increasing the efficiency, again it is a challenging task, right? And again, decoupling the performance of dynamics between the energy source and the utility grid is still a difficult task with the help of power electronics. So that is what we are working on it, to find the solution or to find the overall system performance, right? Yes, this is the schematic of grid-tied solar PV system. As the PV array is basically a variable DC power generation system, that the variable DC is given to the grid as it needs AC. Obviously, this will be interfaced with the help of power electronics converter. So power electronics converter, as it provide an asynchronous interface between the solar PV array and the utility grid, that power electronic converter with associated topology and components with closed loop controller, we are able to meet the requirements of grid connection. That is called a grid connection requirement. As I have mentioned already, that it include active and reactive power control, it include maximizing the efficiency, that include maximum power plant tracking, that include excellent transient response, that include good grid synchronization as well. So the requirements of grid connection, it is possible by implementing a suitable control technique on this particular power electronics converter. So this power electronics converter, it plays an important role in controlling the power delivery, and at the same time ensuring proper integration between the solar PV and the utility grid. Yes, as the configuration, there are two types of configuration in grid-tied solar PV system for a three-phase. One is a single stage, other one is a two-stage. So two-stage grid-tied solar PV system is very popular, as it consists of two converter system. One is a DC to DC boost converter, and other is a three-phase PWM voltage source inverter, right? This DC to DC boost converter, it basically interact with the source, and hence this is what is called a source side converter. Three-phase PWM voltage source inverter, it always interact with utility grid, and it is called a grid side converter. So both has been electrically separated with the help of DC link capacitor, right? And the main role of DC to DC boost converter is to extract the maximum possible power from the PV array by instantaneously controlling the PV output voltage and output current. So we sense PV voltage and the PV current, and that will be given to a maximum power plant tracking controller that will generate corresponding PWM pulses to the boost or buck converter or any DC to DC converter topology. So we are able to extract maximum possible power. Then that maximum power available at the DC link capacitor, that will be further inverted into AC. That AC is controllable AC. That AC is controllable as we implemented PWM voltage source inverter. So by employing an advanced control technique on this three-phase PWM voltage source inverter, we are able to meet all the grid connection requirements. So as we connect a non-linear unbalanced load at the point of common coupling, right? So when you connect an unbalanced non-linear load at the point of common coupling, obviously there must be a problem. There must be a distortion in the grid current. There must be a changes in the voltage at the point of common coupling. There must be a increase in demand or increase in the load demand. Then there must be a problem of frequency deviation as well. So the control algorithm what we employ on this three-phase PWM voltage source inverter, that has to provide proper grid connection requirements. I mean, the control algorithm that has to maintain the voltage profile constant, that has to maintain the grid frequency constant, and that has to, in order to maintain the frequency and voltage, active and reactive power must be controlled independently. And in addition to that, the inverter output frequency and grid frequency both must be synchronized by properly estimating or sensing the fundamental frequency component. All right. Yes, that is what the control strategy, how it is going to be implemented. The grid side converter that can act as a grid feeding device or maybe a grid forming device. So the main role of grid side converter is to manage the DC link voltage constant. As I said earlier, the DC link voltage must be maintained constant because the active power that flows from solar PV to the utility grid, that is what active power P, right? That active power P that governs frequency of the grid. So the frequency of the grid, it must be maintained constant. It means the active power must be controlled or regulated. So the active power must be regulated to maintain the frequency, mean the power balance between the source and the load must be matched or balanced. So if there is a balance between the source power and the load power, then the frequency it remain constant. So that active power balance is possible by maintaining the DC link voltage constant. So of course, the three-phase voltage source inverter with suitable control that ensures constant DC link voltage control. That is what. So the main task is to manage or is to maintain the DC link voltage constant in order to have a proper power flow between solar PV and the utility grid. In addition to that, it injects an controllable active power, AC power, that is in terms of active and reactive power. As I mentioned earlier, active power control is essential to maintain the frequency constant. Reactive power control is essential to maintain the voltage profile at PCC remains constant. The third option may be a grid supporting device, or in terms of voltage, frequency, and power quality, that is called auxiliary requirements. As you can say, the inverter input control is basically a DC voltage control. Inverter output control is basically AC current control and AC voltage control. So any control technique that we employs on AC system that need to have an instantaneous PQ theory, that is called a power theory, or in instantaneous symmetrical components theory, that can be either implemented in stationary reference frame in terms of alpha beta, or in natural reference frame in terms of ABC, or in rotating reference frame in terms of DQ, so that we are able to decouple the active and reactive power components. So these two control must be independent with each other. So this is basically an inner current control, and this must be an outer voltage control. That is what any control technique, it employs cascaded control loop. One is called internal current control loop and the external voltage control loop. So the external control loop, it has to maintain the DC link voltage constant to balance the power flow in the system. And internal current control, it has to regulate the grid current, because grid current has to be controlled instantaneously, because when the inverter output current exceeds its rating, obviously inverter switches are overheated due to overcurrent, then it may easily damage your electronic switches of the inverter. So that internal current control is very essential for overcurrent protection of the inverter switches, in addition to responsibility of power quality issues as well, because we are regulating the grid current. So we are forcefully rejecting all lower order harmonic components, so that the grid current is free from any harmonic presence in the system. That is what the important attributes of inner current control is for harmonic compensation and good dynamics. Whereas external voltage control is essential to maintain the DC link voltage constant. As I mentioned, it is important for maintaining the active power flow in the system. It also important for the system stability with the slow dynamics as well. So the design of inner current control and external voltage external voltage loop is very essential, but still they employ other cascaded control, but still these two control techniques are universally employed in any grid connected inverter system. And you can see the system architecture for grid tied solar PV system, that the solar PV that generates a DC power, that the DC power is given, DC power is extracted by a boost converter with a suitable MPPT controller. That suitable MPPT controller algorithm is developed and dumped in ARM Cortex microcontroller, so that we are able to generate PWM pulses for the boost converter with the MOSFET switch, so that we could be able to boost the voltage with maximum power point tracking. Then that will be available at the DC link. Further, that will be inverted into AC. Then controllable AC is given to the utility grid via interfacing inductor. So this inductor is essential to reject the current harmonic or to reject the current ripple presence in the inverter output current. And here the point at which we are connecting a non-linear load called the point of interconnection or point of common coupling, right? So we sense the load current and the grid current as well as the grid voltages via sensors like a Hall effect sensor. Then that will be fed to DSpace DS1104 control card via analog to digital converter, that is called ADC circuit. Then we are able to implement a control algorithm with the help of MATLAB Simulink. Then that will generate corresponding digital pulses that will be again given to digital to analog converter. Then it is able to generate an analog signal that will be given to real driver circuit, so that we are able to generate the PWM pulses for all the 8 switches. So we could be able to implement a closed loop control on MATLAB Simulink platform with DSpace 1104 microcontroller card. And this is the subsystem design. As we design a solar PV array, as we have designed for 13.5 kilowatts, this must be small k. I am sorry, this was small k. Yeah, this must be a 13.5 kilowatt solar PV and having 3 cells in parallel and 18 cells are in series, having 13.5, I mean module. And the DC link capacitance would be 2257 microfarad in order to have a DC link voltage of 690 volts. And assuming the DC current ripple would be 20% of the actual DC link voltage, and this is what the DC is about 690 volt, having a line to line voltage of 415, assuming the modulation index is about 1, and the coupling inductor should have a 3.31 millihenry in order to reduce the current ripple presence on the inverter output current, and having the current ripple about 20%, and switching frequency assumed to be 10 kilohertz. And this is the boost converter for boost converter design with the duty cycle about 0.21 for increasing the voltage from 539 to 690. So 539 is the output voltage of the PV array. We are boosting into 690 in order to transfer 13.5 kilowatts of PV power to the DC link capacitor. And we assume the ripple current would be 25% of the rated current, as the current is basically a PV output current that it varies instantaneously, so that we can take worst case of 25% of the rated current, and along with the switching frequency of 20 kilohertz of the boost converter switch, we designed the inductor value about 4.52 millihenry. Right? This is the control structure that we are able to decouple the components of active and reactive power with the help of ABC to TQ transformation with the help of power transformation. So this is the power transformation. So we could be able to convert we could be able to transfer ABC to DQ. Now the output current are basically a D and Q axis component that consists of a DC current as well as that consists of average DC as well as oscillating AC component. This oscillating AC component must be rejected, that we use the second order low pass filter, so that only we take average DC component. So this ID is a direct axis component that is responsible for active power control, and IQ is a Q axis component that is responsible for reactive power control. And reactive power control is very essential to maintain the voltage profile, and active power control is very essential to maintain the frequency control. So both control technique is orthogonal with each other. That is what this is basically become a vector control, or I mean stationary reference frame it is a grid voltage oriented control, right? And this is what the control that we implemented in the inner current control and outer voltage control loop. As the PV array output is given to the boost converter output is given to the inverter, it feeds AC power to the grid, the point at which we connect a non-linear load. So we sense load current and three-phase supply voltages and supply current, and it has an outer voltage control loop and inner current control loop, right? So actual DC link voltage that will be compared with the reference voltage, then the error is given to generate DXS component, as it is responsible for active power. And we sense the three-phase AC voltage, then if you are assuming the grid voltage or voltage at PCC it remain constant, it implies Q axis component is 0. So it means under steady state three-phase grid voltage it remains constant, then the grid it doesn't need any reactive power support. I mean the quadrature axis current component is 0, so that it needs only active power control. But whenever there is a deviation in the grid voltage or voltage at PCC, then the IQ component must be injected, as it needs a reactive power support, right? So we have both ID and IQ. We are able to again transfer into ABC with the help of Park transformation, then we are able to generate the reference current, right? So this reference current must be compared with the actual current that is being sensed by the sensor, I mean the Hall effect sensor, then the error is generated. So this error, the reference current error, that will be given to the hysteresis current control with the actual current with the band of plus or minus 0.5 ampere. We are able to generate the PWM pulses for the inverter. We are able to implement a control algorithm. And here we use the grid synchronization in order to decouple APC to DQ. We need the component what is called a phi. That phi is called the phase angle detection. For phase angle detection, we use grid synchronization tool. That we use a space locked loop. You can have an idea. Yeah, yes, we use the phase locked loop. It consists of phase detector and comparator, that is comparator, loop filter, and voltage control oscillator. So we are able to estimate the fundamental phase angle. So the same concept will be used in the electrical vehicle as well. Your position of the rotor, it must be sensed at every moment with the help of any Hall effect sensor. So then that position is very essential to provide proper torque control as well as the speed control of either BLDC motor or switched reluctance motor or permanent magnet motor used in the electrical vehicle. Right. So the synchronization is essential in any electrical drive as well as a grid connected system, for especially for controlling an AC component. Right. So then as we are able to estimate the fundamental frequency, that is essential for decoupling the components. This is what the DC link voltage control reference voltage is compared with the DC link voltage control. Then the error is given to the loop filter and comparator. We are able to maintain a DC link voltage constant with the proper tuning a P and I controller gain, and we have implemented number of optimization technique also to tune the value of gain of P and I very accurately. Okay, this is the power flow equation. We assume that it is like a actual power system, that the power is being transmitted from sending end to receiving end, having the voltage of inverter voltage with the delta and having the receiving end voltage of V grid at a zero angle. So due to phase angle difference, there would be a power flows from sending end to the receiving end having a line reactance of X. You know, the output power that is inversely proportional to the line reactance, so that we could be able to model a grid connected solar PV is a typical power system model. Right. This is what the MPPT technique, all of us know that the point at which we extract maximum power is MPPT. So this point must be always in the equilibrium, having the slope, it must be zero. It implies any changes in irradiation or temperature, this point should not be shifted upwards or downwards. So we employ incremental conductance method, that the change in current with respect to change in voltage, it must be always zero. That is what the slope must be always zero. So if it is positive, it implies that the changes is less than zero. If it is greater than zero, then the slope is negative. But it should be always in the equilibrium point that holds at MPP. Then we are able to implement maximum power point tracking algorithm by satisfying maximum power transfer theorem. Right. This is the laboratory prototype that we have developed in PV research lab at IIITDM Kanchipuram, Chennai, and having the PV panel that we have installed in the outside of the building, and the outlets are available here with 1 kilowatts PV. That the PV power is given to the DC to DC boost converter. Then the boost converter output is given to 3-phase PWM VSI. VSI output will be given to a filter inductor, and then that output should be given to the 3-phase auto transformer. This can essentially act as a point of common coupling, so that we can change the voltage level at the point of common coupling. Then the output is given to the line inductor. Then at line inductor with the PCC, we are able to connect a 3-phase diode bridge rectifier with the resistive load. So this is essentially a nonlinear load, right? And here we have a current and voltage sensor for sensing the grid voltage, grid currents, as well as DC link voltage. Then the algorithm is developed in the host PC in the MATLAB Simulink with the help of DSpace. So the DSpace controller card that interface your actual hardware along with the host PC, so that we would be able to develop a PWM pulses for activating boost converter as well as PWM voltage source inverter. As we use a power quality analyzer to see the harmonic spectrum of the grid current as well as grid voltages. Okay, this is the typical experimental setup that we have made it. And the configuration as what we use with the DSP is called DSpace 1104 control card. The cost would be around 5.9 to almost 6 lakhs. That has been developed by Dynavision so that you can implement any control algorithm in the laboratory prototype, not in terms of product level. This may be especially for validating any experiments in the laboratory prototype. Still we use the D space. That works very fine for inverter or the boost converter that can operate up to 20 kilohertz. This is the system parameter for the simulation and experiment, as the simulation has been considered with the supply voltage of 415 volt with 50 hertz, and these are the system parameters having the PV power output of 13.5 kilowatts. But we have scaled down the values for laboratory prototype. We assume that the supply voltage about 60 volt line to line with RMS having the supply frequency of 50 hertz. Accordingly, the parameters are designed with the PV output power of 500 watts. So we have a different power level from the inverter output, PV output. We took 500 watts only for feeding power to the utility grid with the grid voltage of 60 volt line to line. This is what the simulation study, and you can see till this point, till 0.1 second, without any controller, the grid voltage, it remains sinusoidal. But as we connect three-phase diode bridge rectifier load, your supply grid current is distorted, right? So now as we are connecting a three-phase non-linear load, you can see the waveform is like a staircase. Due to non-linear load connected at the point of common coupling, grid current is distorted. It contains lower order harmonics. So now you see the inverter is not injecting any harmonic current as no controller is employed. But once you employ a controller on the inverter, then it injects a compensating current, and hence the grid current, it becomes sinusoidal and it is in phase with the voltage, right? And at the point of 0.15, still the current increases from certain value to 28.66 ampere, and further it has been reduced. Even during dynamic change in the grid current, still the overall DC link voltage is maintaining constant. I mean, the DC link control, that works very fine to maintain the DC link voltage constant, and it always follows the reference trajectory of 690 volt, right? And in the meanwhile, throughout the case, the grid current is sinusoidal, right? So it means inverter is able to injecting sinusoidal current into the utility grid with the fundamental frequency of 50 hertz. So there must be a proper synchronization between the inverter output frequency and the grid frequency, and moreover, the grid current and grid voltages are sinusoidal, and hence there must be a high demand in unity power factor operation. So grid doesn't need any reactive power support, and you can understand here, as it also contributes for real power sharing, that till the point here the grid is supplying about 20.9 kilowatts, but when the sudden decrement in load, then the grid power reduces. In the meanwhile, the load demand is met by solar PV with 13.49 kilowatts. So PV is also contributing for active power sharing. Yeah, and this is what the transient response. When a sudden change in or sudden increment in load, the current is increases to 34.37 ampere, further reduces to 15.83 ampere. But throughout the case, you can see DC link voltage is maintaining constant. And in the meanwhile, grid current as well as grid voltages become sinusoidal and in phase, and hence the power factor of the utility grid, it remains unity. Right, that is the beauty of proposed control technique. And still, as we uses the four-legged inverter, the fourth leg that is contributing for neutral current compensation, so that the neutral current compensation is possible with the help of fourth leg of the inverter. So hence the zero sequence current component, it absent in the grid current, so that there is no injection of third harmonic current. As we might be knowing from the fundamentals and power system, zero sequence component that meant for third harmonic component. Third harmonic current flows whenever there is a possibility of neutral current flow, because neutral current flows whenever there is the unbalanced current flows between three phases, right? That is the way we are neutralizing the neutral current, right? And this is the experimental results for the cases of active harmonic filtering operation. The grid voltage remains sinusoidal, but the supply current is non-sinusoidal, because we connect a three-phase non-linear diode rectifier load. But with the help of controller, we are able to shape your grid current waveform from higher order harmonic current into sinusoidal, and moreover, current and voltages both are in phase, so that the power factor is unity. Right, this is the compensating current by the inverter. Moreover, DC bus voltage is maintaining constant. And you can see the neutral current without any controller. You can see there is a oscillating current flows in the neutral because of three-phase unbalanced load current. But when the fourth leg of the inverter, it works with the control, then the neutral current is well neutralized with the 0 ampere. Moreover, all three grid current, it becomes sinusoidal, and hence the power factor is unity power factor with balanced three-phase current supplied by the grid. Right, this is the multi-purpose VSC, and still through the same operation, but still we are able to maintain the current sinusoidal, and the DC bus voltage is maintaining constant. And when there is no demand of PV power, then the grid, it supplies 110 watts. But when there is a problem, when the load demand decreases from 110 watts to 102 watts, then the 56.7 watts is supplied by the PV, so that it also contribute for active power sharing. Right, this is the harmonic spectrum. Without any controller, the DHT of the grid current is about 26.5%. But by incorporating a controller and the inverter, it has been drastically reduces to 4.67%. And with multifunctional inverter, it further reduces to 4.40 THT, and the frequency is about 49.9 Hz. Right. And this is the dynamics or transient change during change in non-linear load. Still, overall, the case, the DC link voltage is maintaining constant. And moreover, the current is injected at sinusoidal rate. And moreover, current and voltage both are in phase. Yes, so this multipurpose voltage source converter with the proposed control, it easily attenuate any source current harmonics introduced by a non-linear load. It effectively neutralizes the neutral current with the fourth leg of the inverter, and moreover, it also contributes for active power sharing according to the load demand. So the frequency the system become the frequency stability has been enhanced further. It also eliminates the need for supplementary power filtering equipment to enhance peak use, so that it doesn't need any other filtering or any custom power devices to mitigate power quality problem here. So and hence the inverter is called a multifunctional inverter. Right. Yes. If you have any doubt, please let me know. Am I audible? Dear participants.
Yes, sir. You are audible.
Dear participants, am I audible?
Yes, sir, you are audible.
Dear participants, am I audible?
Yes, sir.
Please won't respond.
Yes,
Am I
sir.
audible?
Sure, sir.
Okay. Thank you. Yeah. And this is the second technique, active current control with the feed forward control loop based control strategy. Here, the three-phase voltage source inverter with the four leg, it is shunted across the three-phase supply line. This is what shunt active power filter. Here, this voltage source inverter, it is acting as a shunt active power filter, as it is powered by a solar PV via via DC to DC boost converter. Right. So here, when a three-phase non-linear loads are connected at the point of common coupling, the new supply currents are distorted. Right. So in order to neutralize the harmonic current presence in the supply current, this voltage source converter, as it is shunted, it acts as a shunt active power filter. It injects compensating current across the line, so that it is able to shape your supply current or grid current waveform sinusoidal. So we sense all three-phase supply current, three-phase supply voltages, I mean the supply grid current, grid voltages, in addition to the three-phase load current and the DC link voltage via current and voltage sensor, and we could be able to feed to DSpace W104 via analog to digital ADC card. Then that generate corresponding pulses on the host PC. As we implement control algorithm and the MATLAB simulink, we are able to generate the PWM pulses for that, and we are able to make it. And here, the control algorithm that we used, active current harmonic control with the help of zero and hold circuit, sample and hold circuit, and zero order circuit. So zero crossing detector. So here it doesn't need any base lock loop for estimating the value of theta. Instead, we used zero crossing detector. That is what we use as unit vector template, so that the control complexity is largely enhanced with the help of this proposed control strategy. And moreover, we employed a feed forward control estimation in order to control the PV output power in terms of PV voltage, PV current, and the terminal voltage, right? So we are able to generate the reference current. Then the reference current will be compared with the actual. We are able to generate all 8 independent pulses. This is the very novel and very new control technique we employed. This paper has been published in IEEE Transactions on Industrial Application 2000 November 2019 issue. You can have a look at the paper. You get complete insight on this control. And this is the simulation response that at 0.21 second, we connected a non-linear load that is called diode bridge rectifier load. The grid current is distorted. At the point here, we employ an active harmonic or proposed control technique. It will shape your grid current waveform sinusoidal, right? As it is injecting compensating current of 15.87 ampere, so that your grid current it becomes sinusoidal. It eventually eliminate all lower order harmonic component. And moreover, the DC link voltage, it remains constant and it always follows the reference trajectory of 690 volt. As the control technique, it ensures sinusoidal current injection, and moreover, it is in phase with the supply voltage or the grid voltage, so that the power factor, it becomes unity. And moreover, during decrement in the load component of the grid current from particular value, the power has been reduced from 20.9 kilowatts to 9.4 kilowatts when the decrement in load. In the meanwhile, the PV is supplying the power about 11.47 kilowatts. So according to that, it also sharing certain amount of power along with the grid, so that the overall energy management performance is better. And moreover, we assume that the grid is the PV is operating at a standard test condition about temperature, it remains constant, but the irradiation that has been reduced from 1 kilowatts per meter square to 300 watts per meter square. Then ultimately, the power produced by the solar PV, it is less. That has been reduced from 11.47 to 3.4 kilowatts, because irradiation is reduces from 1 kilowatts per meter square to 300 watts per meter square, according to this, right? You can see the DC bus voltage stabilization with the control technique existing. You can see the peak overshoot as well as steady state response is very poor, but with the help of feed forward control loop and the proposed control technique, it reduces the peak overshoot. You can see that. And moreover, the steady state response, the steady state error can also be reduced drastically. So that is what this is what the novelty of the proposed study in the paper that has been published, right? These are the system parameters between the simulation and the experiments that we have considered. The simulation with the actual supply voltage of 415 volt line to line, but the experimental analysis we have taken downscaled value about 60 volt 50 hertz supply, and considering the solar PV power of 500 watts. Accordingly, the experimental test bench has been fabricated in the laboratory. We could be able to validate experimentally. This is what the experimental work, that there is no controller is incorporated, then the supply current or the grid current that follows the load current. So it is highly distorted, it is non-sinusoidal, right? That will be injected into the utility grid, that causes power quality problem. With the help of proposed control technique, then the grid current, the harmonics are reduced with the help of injecting what is called that compensating current by the inverter. Then the grid current, it becomes sinusoidal, that it is in phase with the voltage, right? So the power factor has become unity, so that grid doesn't need any reactive power support. And you can see the compensating current waveform. This much amount of compensating current is supplied by the inverter, then the grid current, it becomes sinusoidal. And in addition to that, DC bus voltage profile is also constant, that has been well stabilized with the help of proposed feed forward control loop, right? You can see the resulted source neutral current. So without the fourth leg, the source neutral current is oscillating, and hence the overheating of the neutral wire is there. But with the help of fourth leg of the inverter, then the neutral current is well compensated, that become almost zero. So there is no third harmonic current exists in the grid current. So the grid current, it become completely sinusoidal. This is the response of phase A, phase B, and phase G. So overall, phase G, overall, the grid currents are sinusoidal and in phase with the supply voltages. So the grid is free from reactive power burden. And you can see here without multifunctional inverter and how the source current, with multifunctional inverter, the source current, it becomes sinusoidal and in phase with voltage. So now as the lower order harmonics are eliminated by the proposed control strategy and the grid current, the THD has been reduced to 4.7% from 55.1%. Okay, this is the beauty of the proposed control strategy. So the proposed control technique with the multifunctional inverter, this act as a shunt active power filter that provide power quality solutions when a non-linear load is connected at the point of common coupling. That power quality solution that include source current harmonic compression, suppression, load reactive current mitigation, and source current balancing as well. In addition to that, the fourth leg of the inverter that effectively utilized to neutralize the neutral current so that the zero sequence current components are absent in the grid current. Consequently, this enables the utility grid to deliver only balanced sinusoidal current at the unity power factor. Okay, this is one of the important advantage of the proposed control strategy. So it doesn't need any customized power equipment or power quality device to enhance the power quality. So because this inverter, in addition to provide an active and reactive power control, this also serves as an active power filter, and hence this system is acting as a multifunctional inverter system, right? Moreover, the result presented here, it clearly illustrates that the grid current or sinusoidal that has been injected into the utility grid with improved power quality and also satisfy the THD of the grid current according to IEEE draft 519/2014 standard. I mean, the THD of the grid current that has been reduced from 24.5% to less than 5%. I mean 4.7%. That is well meet the grid connection requirements. Okay, this is another control strategy that we have implemented in the inverter called active current detection method. Here, whatever be the control technique we proposed previously, that having a complexity in the control, and here that complexity has been largely reduced so that it doesn't need sample and holder circuit and zero crossing detector. Instead, we use a unit vector template. You can see that we use unit vector template for generating the reference current for all three phases. That is called WPR, WPY, and WBB. So that this reference current generation is very simple and computationally efficient. This is one of the controls that we proposed and implemented that has been published in International Journal of Circuit Theory and Application, John Wiley. That has been published during March 2021. Right, the proposed control strategy as it uses a unit vector template and in addition to that, it is computationally efficient, so that control is very easily implemented in the control loop with the help of DSpace. Yes, the DC link voltage is sensed by the sensor. Then actual DC link voltage is compared with the reference DC link voltage. Then the error is given to the PI controller. Then the PI controller is able to generate D-axis current component called active current component, and it has to generate the active reference current of active, and further the actual load currents are compared with the reference current. Then we are able to generate the PWM pulses, right? So that we could be able to develop PWM pulses to the inverter. Then the switches, it work very perfectly, so that we are able to control or integrating a solar PV with the utility grid. Yes, and here as I mentioned that this is active current detection method for generating the reference current. It has a very normal mathematical block, less low pass filter besides existing fundamental state of art. Moreover, it detects the fundamental active current component incorporated with harmonics. Subsequently, it has a reduced number of low pass filter from 6 to 3, so that it can be easily implemented even in DSP, TMS320F2812 processor as well. Consequently, the detection of fundamental active current by the proposed IIITDM control, even during grid voltage and load current perturbation, is fast, accurate, which satisfy the remarkable performance. And the first step for generating reference current is the estimation of unit vector template. As we are transferring ABC to DQ component, that the estimation of unit vector, it has a R phase and Y phase and R phase, Y phase, and B phase component, and it has a unit vector template of R phase and Y phase, and B phase is available here. as we are detecting the active current, because active current detection is very essential for, active power control reference current, as we are generating the active current gain, that is for generating the reference current, that is called ILP plus ID, where ID is the reference current based on the unit vector template, and so that we are finally generating the IGR, that is actual grid reference current. So this actual grid reference current is compared with the actual grid current with the help of sensor, then the error is generated, that will be given to hysteresis current controller. Here, hysteresis current controller, then PWM pulses are generated, that will be activating the switches so that we are able to implement the control strategy for proper integration of solar PV with utility grid. Yes, you can see here the power scenario for the simulation purpose, and up to here, up to 0.4 second, as we are connecting a non-linear load, you can see three-phase diode bridge rectifier load, so that the grid current is non-sinusoidal, and moreover, this is the compensating current injected by the inverter, but throughout the case, DC link voltage is maintaining constant at 690 volt. And moreover, the grid power, the PV power, it remains same, but grid power that has been drastically reduced according to the load demand, right? And during that condition, the reactive power of the utility grid is increased when sudden decrease in current, then after it has been stabilized. Right, but overall the power factor that has been maintained constant, but during the dynamic cases the power factor that has been reduced slightly, but overall the power factor is good. It is almost unity power factor. And when the sudden change in irradiance that happens, you can see the sudden increase in irradiance, then the grid power is increasing, but the change in irradiance from 1 kilowatts per meter square to 300 watts per meter square, then the grid power, PV power, that reduces. But still, during that condition, as the grid power demand is increasing, then that it also needs the reactive power support to maintain the DC link voltage constant. And that is what during DC link voltage control, the grid, it needs a reactive power support. But when the power balance is maintained, then the DC link voltage is constant, then the grid doesn't need any reactive power support, then the power factor can also become unity power factor. Yes, you can see here the DC link voltage stabilization during sudden decrease in load, because when the DC link voltage increases, the DC link voltage increases when the load demand is less than the PV power. So when the load demand is less, that time the DC link voltage increases. But still, that DC link voltage that should be bring back to the actual reference voltage of 690, right? And this is what the actual, the dB, this is the reference voltage 690. Then the SRF based control, still the peak overshoot is very high, and moreover settling time as well. Then the control that we proposed in the reference 23rd, still the overshoot is bit more, moreover settling time is also a bit more. But proposed IIITDM, almost peak overshoot and settling time is largely reduced. That is what the DC link stabilization is excellent in this proposed control strategy. And also how the reference current we are generating based on the step response, you can see the black is a proposed IIITDM. Proposed IIITDM, exactly it follows the reference, so that the error is largely reduces, so that the grid current is exactly estimated without any error, then the overall control loop, it works excellent. Right, see the grid voltage is sinusoidal, grid current is also sinusoidal, but the load current is non-sinusoidal, that we are connecting a three-phase diode bridge rectifier load. To have a proper power quality improvement, the inverter is injecting a compensating current, right? So here the both PV grid current that is in phase with grid voltage, so that the power factor will become unity. And you see the response of the load current is still staircase as we connect three-phase diode bridge rectifier load. And the DC link voltage is constant, and the reference current is almost, the error is 0, and in the meanwhile power factor it become unity. Right, for all the cases you can see the you see the harmonic spectrum. The harmonics is the fundamental 50 Hz only, it is injecting, but see the response for all the cases, how the DC link voltage is maintaining constant. See, throughout the case, the DC link voltage is maintaining constant with that, and moreover, grid current is in phase with the grid voltage, and moreover, grid voltage, DC link voltage is maintaining constant, right? And this is what the things, but still the THD has been reduces from 20.1% to 4.64%. This is with controller, this without this the without controller, that is still fifth order harmonics, seventh order harmonics are dominating, but with the controller that has been reduces to 4.64% with negligible lower order harmonic component. And with multifunctional inverter operation or ACDM, active current detection method of control, further reduces to 2.91%. So it with negligible lower order harmonic component, it injects only the fundamental current component of 50 Hz. This is the comparative analysis with the proposed control, and this is the control that we published in IEEE Transactional Industrial Applications. This is what the state of art research with PLLS, fast current tracking control, and this is the SRF based control. But overall, the proposed control that ensures overall system performance. I mean, THT is 2.91%. Sampling time is about 30 microsecond. It means the microprocessor or the DSP, that response time is largely reduced. In the meanwhile, it needs only 3 low pass filters, so that the algorithm is computationally efficient, that can be easily sampled at even at low switching frequency, and precision is very high. Moreover, it's not complicated for implementation. Still, you can implement it with the DS1104. And the calculation, that is what, as it reduces the mathematical equations for mathematical modeling of the proposed control, and grid synchronization, we used unit vector template, as it doesn't need any SRM based PLL. Overall, the robustness is very fast dynamic response, and this for the case of grid voltage with either ideal or non-ideal. I mean balanced as well as unbalanced three-phase AC voltages with a non-linear load. This proposed approach is very, very effective. As I come to the conclusion that the proposed control algorithm has been capable of performing dual functionality of power quality improvement as well as active power injection. In addition to that, DC link voltage controller is control that has been observed with very faster stabilization, so that it improves the overall transient response of the system with reduced peak overshoot and under overshoot. And the proposed IIITDM is very simple in structure, because we used only 3 low pass filters, sample and zero crossing detector and sample and hold circuits are largely eliminated as compared to state of art control technique that has been proposed in the recent literatures. And overall, the design system offers higher detection speed. I mean, the response time is very faster, and it is very accuracy in control during steady state as well as in the transient condition. So this is the paper we published in International Journal of Circuit Theory and Applications. So these are the key references that we could come across. Still, the reference number 3 that we published in IEEE Transaction and Power Electronics with the title Features of Power Quality in Single Phase Distributed Power Generation Using Adaptive Natural Vectorized Filter, that we published in IEEE Transaction and Power Electronics. Even day before yesterday, one of the paper got accepted in IEEE Transaction and Instrumentation and Measurement relevant to grid synchronization, as we proposed a new novel base locked loop based what is called base detection technique or grid synchronization of grid-tied solar PV system. So likewise, our team is under my supervision. There are 4 research scholars are working with a different domain in the grid-tied solar PV system, including solar PV system design and modeling and partial shading and reconfiguration at MPPT. Another one of my scholar is working on control and grid integration of grid-tied solar PV system, that what we presented. And another one of my scholar is working in grid synchronization of, development of novel grid synchronization algorithm for grid-tied solar PV system. Another one of the scholar is working on energy management system in smart building with the help of built-in integrated PV model. Okay, and hope you might have enjoyed this session on advanced control techniques of grid-tied solar PV system. So this is open to audience. So if you have any doubt, please let me know. Thank you for your kind attention.
Participants are requested to ask the queries.
Yeah, if you have any doubt, please let me know.
Sir, what is the difference between grid forming inverter and grid feeding inverter?
Grid forming inverter and grid feeding and grid forming, right?
Yes.
Grid feeding mean what we have discussed, what I have delivered a talk here, that is exactly grid feeding. Grid feeding mean inverter output power that will be injected into the utility grid. All right. Grid forming mean the inverter is a form, it is a part of the grid that may be applicable in the microgrid structure. Right. If the microgrid structure that says the concept of both isolated mode as well as grid connected mode, right? If it is in isolated mode, then inverter that feeds power to the load without any supporting from the grid, right? So during that condition, inverter can also act as a part of the grid as the load power is independent of the grid power. But we are talking about the grid feeding mean as we are feeding power to the utility grid via inverter from the solar PV. This is basically a grid feeding. Okay.
Thank you, sir.
Yeah. So far, and moreover, the control tasks are totally different for both grid connected as well as microgrid system. And here we discussed only on grid connected inverter system, not microgrid control system. Because microgrid control means the control is completely different. That is based on the droop control. Because when the local loads are depends on the inverter output, then there may be a very dedicated control technique that ensures frequency and voltage constant. That is the difficulty in the standalone system. But here we discussed only on grid connected solar PV system. Okay.
Any more questions from audience?
Yeah, if you have any doubt, please let me know. I'll clarify your doubt.
Yeah.
Sir, I'm Venkateshan. Really, it's more informative, sir. Thank you. And I have one small doubt, sir. Sir, as you said, a gallium arsenide PV cell having a higher efficiency around more than 18 to 25%.
You are not audible. Am I audible?
Yes, sir. Yes, sir. So now it is audible, sir.
I couldn't be able to get anybody's voice. Yeah. Now you are audible. Hello?
Sir?
Yeah, you are audible now. Please tell me.
Yeah, sir. Really, it's more informative, sir.
Yeah,
Thank you. And I have only one small doubt, sir. That you said gallium arsenide cell having a higher efficiency than the polycrystalline and the monocrystalline.
Yeah.
Why gallium arsenide not famous, sir? That's my small question.
Yes, it is not famous. Still, it is under development. So I didn't mean that it's a mature technology. Still the silicon is a one man. It is a kind of one man army that plays a role in semiconductor industry. Why gallium arsenide or indium phosphide or any compound semiconductor materials are not so popular? The issue is in the fabrication. There would be a fabrication issues with this compound semiconductor material. That is what not so popular. Still it is under development. It is a proven technology that it can enhance the cell efficiency from 15 to 30%, but that the cells are not commercially available. The problem is with fabrication. Understand?
Okay, sir. Okay, sir.
Yeah, in addition to that, the leakage current issues also, because leakage current is also another problem associated with the solar PV. And the leakage current, as again you might be knowing that the leakage scale is directly proportional to the temperature, right? Yeah. And so still the research is going on how to enhance the cell fabrication technique.
Okay, sir. Thank you.
Yeah, that is what silicon cells are still popular. They dominate semiconductor industry.
Sir, one more question.
Yeah, please.
So what is the role of multi-level inverter in Grid integration.
Multi-level inverter, whatever we implemented with a simple two-level PWM voltage source inverter or matrix converter or Z source inverter or having number of converters, you know, the final purpose is to what? That is what I mentioned. The problems associated with the modern power system is what? Whatever be the solution you are finding, but final solution should be cost effective, right? The cost effective mean either you can use two-level PWM VSI or three-level PWM VSI or multi-level or matrix converter or Z source inverter. What would be the overall system cost, right? That overall system cost that depends on the power rating as well. So if you talk about the power rating about 20 kilowatts grid connected or even 50 kilowatts grid connected system, still two-level inverter that performs better and over the cost is less. But where we are not concerned about the sinusoidal grid current, but whereas once you implement multi-level inverter based grid connected PV system, that is for high power application, maybe the power rating in terms of megawatts level, because multi-level inverter they developed exclusively for high power application in terms of megawatts power range. First thing. Second thing is what? Multi-level inverter can inject this current sinusoidally as we are increasing the number of level, so that the voltage across the each switch that has been drastically reduced. Moreover, we use small size DC link capacitor. You know, because we are stepping down, we are using the multiple cells or multiple switches are in series parallel, so we reduces the stress across the DC link capacitor. Okay, that is one of the advantage of the multi-level, but still we are increasing the number of level with more number of switches. Of course, the cost of the inverter is quite expensive. That is why multi-level inverter or a dedicated inverter system for high power applications, not for low power or medium power applications. Okay.
Thank you, sir.
Yeah. Hope you understand. Nowadays, even multi-level inverters are very popular for even wind energy, having the power rating in terms of megawatts level. Yeah.
Sir, one more question.
Please.
Sir,
Yes, please.
is there any solution to reduce the instability mode of tracking the maximum power point, sir?
It is not in terms of instability, madam. See, your PV is exposed to the sun. The state of art of the solar energy is temperature and irradiation. Due to sudden change in temperature and irradiation, output changes abruptly, so that we need to extract maximum possible power even at low irradiance. That is what we are proposing, any MPPT technique. But the challenge in extracting the maximum power is at low irradiance condition. For example, there would be a kind of heavy snow, or there would be a kind of the partial shading. If during that condition, tracking the maximum power is a very difficult task, because we use power electronics converter as it satisfies the theorem called the maximum power transfer theorem, right? So, the stability point of view, sudden increase in irradiance or sudden change in irradiance, then MPPT has to adapt, right? Then MPPT should be an adaptive algorithm. Then possibility we can enhance the overall system stability, and also we can track the maximum possible power with good transient response. Understand? That is what even now many cases all classical MPPT algorithm that fails to detect track maximum power at low irradiance or during abnormal condition. Almost more than 200 algorithms are available in the literature. Maybe you might have come across. So extracting the maximum power during low irradiance or during partial shading is a very difficult task. And another thing also, what if the solar cells are partially shaded, and that may also causes the overheating of the solar due to a hotspot. And again, there would be a design of a bypass diode. In addition to that, there is a problem associated with leakage current as well. So the many factors are involving, and studying and implementing maximum power point tracking in the real time, I mean in the real system. Hope you understand.
Yes, sir.
Okay. Yes, any other doubt?
Sir, is it possible to apply machine learning concept in grid integration, sir?
Machine learning grid integration, we can employ on parameter estimation or forecasting of solar PV. So if you wanted to forecast the solar PV, either in terms of short term or mid term or long term, we employ machine learning as well as artificial intelligence. So in terms of control, I don't think so. Your machine learning techniques are essential. That is essential for forecasting only.
Okay, sir. Thank you.
Yeah. Because still many researchers are working on forecasting as well. Solar energy forecasting in either in terms of short term or mid term or long term. You know, one of the difficulty encountered in the solar PV is a forecasting. So forecasting is a big issue. You might be knowing that today in a TV, in the weather forecast, they tells that today 6 o'clock there would be a possibility of rain. But once you reach 5 o'clock at the evening, you may not feel much heavy rain. So it implies that the forecasting fails sometimes. So especially on solar photovoltaic, forecasting the solar energy is a very difficult task. That is what nowadays they employ intelligent technique or a machine learning technique to forecast the solar energy on the particular location. Now they are able to implement the machine learning technique. I come across few papers on solar forecasting using machine learning technique or artificial intelligence as well.
Thank you, sir.
Yeah.
Any more questions from audience?
Okay, thank you very much. Still, if you have any doubt, you can find my profile. You can send me an email. I will clarify your doubt. Again, we will meet on 10th. I am going to give another impressive lecture on peer-reviewed model and the publication process in peer-reviewed journal. Okay, that would be very beneficial for the early career researchers. So please all attend that session. It will be very beneficial for your PhD. Okay, thank you very much. And thanks organizing team to invite me and for this proposed FTP. And hope you all might have enjoyed the session. So looking forward to meet you again on day after tomorrow. And thank you very much. And thank you, Mr. Balamurugan and our coordinator. Okay, thank you again. Yeah.
Thank you very much, sir. Of course, you have proven the role of power electronics in the power system as well as in EV system. Thank you for your valuable session. Thank you, sir.
Okay. Thank you very much. So hoping to meet you on day after tomorrow. Okay. Thank you, Dr. Nageshwari.
Yes, sir. Thank you, sir. Thank you, sir.
Okay.
Thank you so much, sir. It is very informative session, sir.
Okay.
We enjoyed a lot.
Okay. Thank you very much.
Thank you, sir.
Yeah. Should I leave the session?
Yes, sir. Sure. Thank you, sir.
Okay.
One small announcement to the participants. So there is a slight change in the program schedule. As per the previous schedules, tomorrow afternoon session is healthy lifestyle behavior modifications through fitness. But this session is rescheduled to 10th December afternoon. So just an interchange of afternoon sessions. So this change has been made on the request of your resource person. So I think I am audible to you, isn't it? So as per the revised schedule, tomorrow forenoon session is hands-on session on powertrain design and electrical motor parameters simulation for EV. Tomorrow afternoon session is research and entrepreneurial opportunities in electrification beyond mobility. So since we have hands-on session tomorrow morning, software needed for the hands-on session are LabVIEW 2018 and Multisim 14.1. So if you have the software, you can use it. Otherwise, you can download the trial version and the links will be shared in the chat box. The same link will be shared in the WhatsApp group also. So I think the links are shared in the chat box. You can note it down. You can copy, you can paste in your system. So the same links will be shared in WhatsApp group also. You can use it. So if you want, the demo session will be there tomorrow morning. Parallelly, you can work it. So these two are trial versions of this. So the link for attendance also will be shared in chat box. You can fill the attendance and feedback form. If you have any suggestions for the improvement of the event, you can say you can unmute, you can say, or you can express your views in chat box, or you can express your views in WhatsApp group also. If you need any improvement for the event, you can express your views. So assessment link is shared in chat box. You can take it. Final assessment. So today's attendance cum feedback form is shared in chat box. You can fill it. Vidya ma'am, what did you ask? What about assessment means? Today's attendance link you want? Are you asking final assessment, ma'am? Final assessment will be at the end of the FDP, at the end of the last session, Friday afternoon. Thank you all the participants. We shall meet tomorrow morning at 9:30 a.m. as usual. Thank you once again.